Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, so let's unpack this because for basically the entirety of human history, looking up at the moon has been this exercise in, romantic isolation.
Right, yeah, it's the untouched wilderness.
Exactly. You look at that silver disk and it represents this poetic silent rock.
Yeah.
But I really want you to just erase that image tonight. Because when you look up now, you aren't looking at a silent wilderness. You are looking at a booming, highly capitalized, and incredibly active construction site.
Oh, absolutely. It's a complete paradigm shift.
Yeah. The physical, technological, and honestly, the economic foundation for a permanent human neighborhood is being poured right now. And the sheer scale of the capital being deployed to do it is just staggering. We are fundamentally shifting from science fiction into the gritty world of, municipal planning in a vacuum.
We really are. The era of exploration, that whole Apollo mindset of planting a flag, leaving some footprints, and coming right back home, that is entirely over. What we're witnessing right now is the deployment of permanent infrastructure. And to really grasp the mechanics of this shift, you have to look at the structural overhaul of how we move mass off this planet.
Which has always been the bottleneck, right?
Exactly. For decades, the dominant model was the monolithic, government-designed spacecraft. It was exquisite, custom-built, slow, and just astronomically expensive. You just can't build a permanent expanding base using these bespoke one-off vehicles.
Right. I mean, if you're building a skyscraper in Manhattan, you don't commission a team of engineers to design and build a brand new custom delivery truck from scratch every single time you need a load of steel.
No, of course not.
You just hire a logistics company that already has a fleet, like FedEx or UPS.
And that is exactly the pivot NASA has made here. They have essentially decided to stop building their own delivery trucks. They are now hiring the lunar equivalent of FedEx to handle the freight.
It's just wild to think about.
It is, and the underlying economics of that decision are fascinating. We are looking at a nearly $600 million investment, specifically targeted at 4 commercial moon landings. And all of these are scheduled to touch down in late 2028.
So this is part of the CLPS initiative, right? The Commercial Lunar Payload Services.
That's the one. And the distribution of that capital tells a very specific story about redundancy and competition. So you have Astrobotic receiving $297.9 million to execute 2 separate surface deliveries.
Wow.
Yeah. And then Firefly Aerospace was awarded $144.2 million for one delivery, and Intuitive Machines is getting $148.3 million for another.
But here is the thing that really stood out to me when looking at the architecture of these 4 missions. They aren't unveiling some radical, never-before-seen sci-fi spacecraft.
No, not at all.
They are explicitly using upgraded versions of landers that have already flown, which, from a PR standpoint, maybe that sounds less exciting. But from a logistics standpoint, it feels incredibly pragmatic.
Well, pragmatism is literally the only way to survive the tyranny of the rocket equation. Ryan Stephan, he's the acting director of cargo landers for the moon base. He framed this beautifully. He characterized this entire operational phase as a proving ground. But the key metric he highlighted wasn't thrust or, payload capacity.
Right.
It was ordering cadence.
Ordering cadence, meaning the actual frequency with which they can just swipe the credit card and put a box on the moon?
Exactly that, because the traditional spaceflight model meant waiting 10 or 15 years between missions. If a single valve stuck or a sensor degraded under radiation, the entire program would just grind to a halt for a multi-year redesign.
Right, totally paralyzing.
But the commercial competition model flips that. If an Intuitive Machines lander has a thruster anomaly, they don't scrap the whole architecture. They pull the telemetry, tweak the upgraded model, and they fly the next iteration a few months later.
Let's run the numbers on that cadence, though, because this is where the sheer volume of traffic becomes real to me. We are talking about 17 lunar surface deliveries already on the books.
17. It's incredible.
17. If you map that out over the next decade, the phrase lunar highway isn't just some cute metaphor. It is a literal description of the orbital mechanics between Earth and the moon right now. We are moving away from these historic, world-stopping events into basically a scheduled transit system.
And this is but a scheduled transit system built on a decentralized commercial fleet introduces a massive scientific and engineering headache.
How so?
Well, think about the variables at play here. Astrobotic, Firefly, and Intuitive machines are all utilizing highly proprietary delivery vehicles. They have different structural geometries, different engine thrust profiles, different propellant mixtures, and vastly different autonomous descent software.
Oh, right. And they aren't all landing at the same spaceport either. They were targeting entirely different regions of the lunar surface.
Exactly.
Like, Astrobotic might be putting down near an equatorial mare, while Firefly is targeting a heavily cratered plateau near the South Pole.
Which means the physical interaction between the vehicle and the lunar environment during touchdown is going to be completely unique on every single flight. So if you're NASA and you are trying to gather reliable, actionable engineering data to design your future permanent habitats, how do you account for all those vehicle-specific variables?
Yeah, that makes sense. Like, if a sensor spikes on the Firefly lander, was that caused by the unique geology of the South Pole? Or was it just a weird vibration resonance from Firefly's specific engine design?
Precisely. You have no way of knowing unless you have a control.
Okay, wait. I have to push back on the solution to this, though, because payload mass is the single most expensive commodity in the solar system.
Yeah.
Every gram you lift out of Earth's gravity well costs thousands of dollars.
It does.
So NASA's mandate, their solution to this data problem, is to force all 4 of these late 2028 flights to carry the exact same trio of science instruments. Yeah. But if we already know the instrument works on the first flight, flying the exact same mass 3 more times feels like a staggering redundancy, doesn't it?
Yeah.
Like, why burn millions of dollars in payload capacity just to replicate the cargo?
Because without that replication, the data is essentially worthless for building predictive models. Joel Kearns, the Deputy Associate Administrator, likened this strategy to deploying a network of weather stations.
Great.
If you build the most sophisticated weather station on Earth and put it in Chicago, you still know absolutely nothing about the global climate. You only have localized data for Chicago.
Right, but you wouldn't put 4 weather stations in Chicago.
No, you put one in Chicago, one in the Sahara, one in the Amazon, and one in Antarctica. But, and this is the critical part, you have to make sure all 4 stations are using the exact same brand of thermometer and the exact same anemometer.
Oh, I see.
Because these landers have different thrusts, use different fuels, and are landing in different topographies, the scientific method actually demands a standardized control payload. By flying the identical instruments on all 4 missions, they isolate the lander as a variable. They aren't just taking isolated readings anymore. They are creating a baseline.
A baseline for the new neighborhood. I love that. And that actually brings us to the first of these 3 mandated standardized tools, which is designed to tackle the most chaotic, violent, and just immediate threat to any lunar infrastructure.
The landing itself.
Exactly, the final descent.
Right, the interaction between the exhaust plume and the regolith.
Here's where it gets really interesting. Let's talk about the physics of that interaction, because I think a lot of people picture a lunar landing, like, a helicopter touching down in a desert. Yeah. The dust billows up in these big, fluffy clouds, swirls around a bit, and eventually settles.
That's the movie version.
Yeah. But the reality of a lunar landing is closer to a sustained microscopic explosion.
It really is. We have to completely discard our earthbound intuition about how dust behaves. On Earth, sand and dirt are the products of millions of years of continuous weathering. They're tumbled by rivers, blown by atmospheric winds, ground down by glaciers.
So they're soft.
Yeah, the edges of a grain of sand on Earth are generally rounded and smooth.
But on the moon, you have a hard vacuum. No wind, no rain, no atmospheric friction?
None. The lunar regolith was created over billions of years by micrometeorites slamming into the basaltic surface at hypervelocity. They basically shattered the bedrock into microscopic fragments. And because there is no weathering process to smooth them out, those particles remain incredibly jagged.
Wow.
They are essentially microscopic shards of razor-sharp glass.
And beyond the shape, there's the electrostatic charge.
Yeah.
Right? Because there's no atmosphere to shield the surface from solar radiation, the sun's ultraviolet light knocks electrons off the dust particles, giving them this strong positive charge. So they repel each other, but they cling desperately to literally anything they touch.
Exactly. Now introduce a chemical rocket engine into that environment. When a lander fires its descent engines to bleed off orbital velocity, it isn't blowing air. It is expelling superheated gas at thousands of meters per second into a vacuum.
Which is terrifying.
Right, because on Earth, the atmosphere provides resistance, which causes the exhaust to billow and swirl into those fluffy clouds you mentioned. But in a vacuum, there is no atmospheric pressure to push back. So the exhaust expands outward radially, incredibly fast, and completely parallel to the ground.
So it picks up these electrostatically charged microscopic glass shards and accelerates them outward at supersonic speeds. It's not a dust cloud at all. It's a continuous 360-degree shotgun blast.
That is the lunar plume, and we know exactly how destructive this is because we've actually seen it.
During Apollo, right?
Yes, Apollo 12. Pete Conrad and Alan Bean executed a precision landing of the Intrepid lunar module about 160 meters away from the robotic Surveyor 3 probe, which had landed there a few years prior. And when they walked over to inspect Surveyor 3, they found that the exhaust plume from their own landing had completely sandblasted the probe. It pitted the metal and deeply scored the optical lenses. And that was despite being over a football field away.
And that was just a tiny Apollo descent stage. Now we're talking about landing massive commercial cargo freighters, eventually followed by multi-ton habitats and extraction machinery.
It scales up the danger exponentially.
If you land your supply freighter too close to your permanent solar array, your own engine exhaust will strip the protective coatings right off the panels and permanently blind all your optical sensors.
Which is exactly why the first standardized instrument is absolutely critical for base planning. It's called the stereo camera for lunar plume surface studies, or SCAL-PSS.
I love when engineers clearly work backward to create a good acronym. SCAL-PSS, it is memorable at least. But the engineering inside SCAL-PSS is brilliant. It utilizes an array of 4 cameras mounted around the base of the lander, and it employs stereophotogrammetry. Okay, let's break down how stereophotogrammetry actually works in this context.
Yeah.
Because they aren't just taking a cool GoPro video of the dust flying around.
No, they are measuring the physical volume of the crater being excavated in real time. By having 4 cameras with overlapping fields of view, SCAL-PSS uses parallax, which is the same principle our 2 eyes use to perceive depth.
Yeah.
So as the engine fires and the gas begins displacing the regolith, SCAL-PSS takes continuous simultaneous images. The software then analyzes the slight differences in perspective between the cameras to calculate the exact distance to millions of individual points on the ground below.
So it's basically mapping the erosion as it happens.
Exactly. It creates a high-fidelity, 3-dimensional topographical map that updates multiple times a second during the final seconds of descent. It shows exactly how deep the thrust is digging into the surface, the angle of the trench being carved, and the total mass of the material being ejected.
And because NASA is forcing Astrobotic, Firefly, and Intuitive machines to all carry SCAL-PSS, they get this 3D data across a massive variety of variables.
Right.
They get to see how a continuous throttle engine excavates dust compared to, like, a pulsed engine. They see the difference in plume dynamics when landing on compacted equatorial regolith versus the looser, colder soils at the South Pole.
And they are feeding all of this data into fluid dynamics supercomputers to build a universal predictive model. Because if you want to build a permanent moon base, you need zoning laws.
Zoning laws, yeah.
You need a mathematical certainty that tells you, if we place our habitat here, the landing pad for the supply rockets must be exactly 800 meters away behind a topographical berm to ensure the habitat doesn't get shredded by supersonic glass.
Okay, so SCAL-PSS solves the landing hazard. It allows us to mathematically zone the base, the violent descent is over, the engine's cut off, and the microscopic glass storm finally settles. But now you have a multi-million-dollar lander sitting in the middle of a barren, gray, hyper-extreme environment. The next massive logistical hurdle is knowing exactly where you are.
Right. Navigation without infrastructure. On Earth, we take absolute location for granted. We have this constellation of dozens of GPS satellites constantly broadcasting highly precise timing signals that allow our phones to triangulate our position down to a few meters.
But the moon has no GPS.
The moon has 0 GPS.
And beyond that, the visual landmarks can be incredibly deceptive, right?
Yeah.
The lack of atmospheric haze completely messes with human depth perception. A mountain that looks like it's a 2-hour hike away might actually be 50 miles distant.
Oh, absolutely.
And the shadows cast by the sun in a vacuum are absolute pitch black. They completely hide craters and ravines. You can't just look out the window and draw an X on a map.
Which is why the second standardized payload is so deeply elegant. It's called the Laser Retroreflector Array, or the LRA.
This is perhaps my favorite piece of technology in this entire discussion, because when you read the technical specs, it sounds absurdly low-tech compared to the rocket it's riding on. We are talking about a device roughly the size of a cookie.
Just a little cookie.
It's a hemispherical aluminum frame, and embedded inside that dome are 8 tiny quartz corner cube prisms, and that's it.
Well, the brilliance of the LRA is precisely its lack of complexity. When you engineer systems for deep space, complexity is your worst enemy. Active systems require power. Batteries freeze during the 14-day lunar night when temperatures drop to negative 200 degrees Celsius.
Right.
Solar panels degrade from radiation. Electronic circuits get fried by cosmic rays. The LRA has 0 moving parts. It requires absolutely 0 electrical power. It is an entirely passive piece of optical geometry.
So in the middle of all this billion-dollar high-tech rocketry, we are basically leaving behind a highly engineered, immortal bicycle reflector.
That's exactly what it is. What's fascinating here is the sheer resilience of passive technology in the brutal environment of space.
But wait, how does a corner cube prism actually work? Why not just use a flat mirror?
Good question. If you shine a laser at a flat mirror, the light bounces off at an angle equal to the angle it struck. So if you are orbiting the moon in a command module and you shine a laser down at a flat mirror on the surface, unless you are perfectly perpendicularly aligned directly above it,
The laser will bounce off into deep space.
exactly, you'll never see the return signal.
But a corner cube is different.
Very different. A corner cube is essentially the inside corner of a perfect glass box, 3 mutually perpendicular flat surfaces. Because of the geometry of those 3 angles, any light that enters the prism bounces off all 3 walls and is reflected back on the exact same vector it arrived on.
Oh, wow.
It does not matter what angle the spacecraft is at when it fires a laser. The light always returns straight to the source.
So a future incoming lander or an orbiting satellite could just sweep the surface with a laser altimeter. The moment the laser hits that cookie-sized LRA on the ground, the photon packet bounces straight back to the ship's sensor.
And because we know the speed of light is a constant, the ship's computer simply measures the time of flight, the microscopic fraction of a second it took for the laser to travel down and back. That single measurement instantly gives the spacecraft its exact distance from that specific fixed point on the lunar surface.
But there has to be an engineering catch here. If it's just quartz and aluminum, how does it survive the thermal expansion? The moon swings from boiling hot in the sun to hundreds of degrees below zero in the shade. Wouldn't the aluminum frame contract in the cold and just crush the quartz prism?
That is the exact thermal engineering nightmare that went into designing the housing. The quartz prisms are actually floating within the aluminum dome.
Really?
Yeah, they are held in place by highly specialized retention rings that absorb the different coefficients of thermal expansion. So the aluminum expands and contracts violently with the temperature swings, but the quartz prisms remain isolated and perfectly aligned.
It is the ultimate long-term municipal investment. By forcing every single one of these commercial landings to bolt an LRA to their roof, NASA isn't just navigating these specific missions. Long after the Astrobotic or Firefly landers have completely died, their batteries dead, their circuits fried, just sitting there as silent monuments, those quartz prisms will still be functioning perfectly.
We are laying down a permanent, fail-proof navigational grid. 10, 20, or 50 years from now, when the lunar transit highway is crowded with autonomous cargo freighters, they won't be landing blind. They will be using the LRA grid established by these 2028 missions to triangulate their descent profiles down to the millimeter.
Okay, so we've mapped the destructive physics of the landing plume with Skello PSS. We've laid down the immortal location grid with the LRA. We can land safely, and we know our exact coordinates. But now we have to deal with the most fragile cargo of all.
Biology. The human element.
Yes, because the lunar surface is a profoundly toxic environment for organic chemistry. We often get caught up in the romance of space travel and forget that the universe is constantly throwing invisible, highly charged energy at you, basically trying to kill you.
It is actively hostile. We take Earth's magnetic field for granted. The dynamo generated by Earth's molten iron core creates a massive magnetosphere that acts as a planetary deflector shield. It redirects the vast majority of the lethal solar and cosmic radiation safely around the planet.
But the moon has no active dynamo.
Right. It has no global magnetic field. It is completely naked to the cosmos.
Which brings us to the third standardized instrument, the Linear Energy Transfer Spectrometer, or LES. And to understand what LES is measuring, we need to categorize the two distinct types of radiation bombarding the lunar surface, right?
Correct. The first category is solar particle events, or SPEs. These are driven directly by the sun. During a solar flare or a coronal mass ejection, the sun expels a massive wave of highly energized protons. These events are somewhat directional, and they can spike incredibly rapidly.
So if an astronaut is caught outside on the lunar surface during a severe SPE without adequate physical shielding,
The acute radiation poisoning can be lethal within hours.
that's horrifying. So that's the localized weather of our solar system. But the second type is arguably much more terrifying because of where it comes from.
Yes. Galactic cosmic rays, or GCRs. These do not originate from our sun. GCRs are heavy, high-energy ions, often the nuclei of atoms like iron or carbon that have been stripped of their electrons and accelerated to nearly the speed of light by cataclysmic events outside our solar system, like distant supernovas.
Basically microscopic cannonballs.
That's a very apt description. Because they possess such immense kinetic energy, they are incredibly difficult to shield against. When a GCR smashes into the aluminum hull of a spacecraft or, the fabric of a spacesuit, it doesn't just stop. It shatters the atoms of the shielding material, creating a secondary shower of highly energetic subatomic particles that continue inward.
Oh, I see.
And when those particles strike human tissue, they sever the bonds of DNA strands, leading to long-term severe health consequences like cancer, central nervous system degradation, and cataracts.
So how does LES actually measure this invisible barrage? The documentation notes it relies on a compact, solid-state silicon detector. But how does a piece of silicon tell you what kind of radiation is hitting you?
It all comes down to the physics of semiconductor junctions. The silicon in the LES sensor acts like an electronic tripwire. When a high-energy particle, whether it's a proton from the sun or an iron nucleus from a supernova, passes through the silicon lattice, it violently knocks electrons out of their orbits. This creates what we call electron-hole pairs.
So it essentially generates a microscopic electrical charge inside the silicon.
Exactly. And the magnitude of that electrical charge is directly proportional to how much energy that specific particle deposited into the silicon as it passed through. This is the linear energy transfer the instrument is named for. So LES doesn't just buzz like an old-school Geiger counter to say, warning, radiation. It measures the exact energy profile of every single particle strike.
Meaning it can differentiate between a barrage of solar protons and a heavy strike from a galactic cosmic ray.
It maps the localized radiation environment with incredible fidelity. And by flying LES on all 4 of these different commercial landers, we can finally answer the critical questions about secondary radiation. Like, does landing inside a deep crater provide natural shielding against GCRs coming from the horizon?
Right.
Or does the chemical composition of the regolith at the South Pole generate more secondary particle showers when struck by radiation than the regolith at the equator?
We have to know those answers before we pour the concrete for the habitats.
Mm-hmm.
I mean, if the secondary radiation shower from the regolith is too high, you can't just pile dirt on top of your habitat to protect the crew, which has been a leading theory for base construction for decades.
Exactly. The LES engine directly dictates the engineering pipeline for the entire Artemis program. It tells the material scientists exactly how thick the walls of the pressurized rovers need to be. It tells the spacesuit designers what kinds of hydrogen-rich polymers they need to incorporate into the fabric to absorb those heavy ions.
It's all infrastructure. Skel PSS maps the dust so we don't destroy our own hardware. LRA lays down the immortal navigation grid so we don't get lost. LES maps the radiation hazard so we don't inadvertently poison the crew. These 3 instruments are the advanced scouts.
They are.
But NASA isn't just planning for the scouts. They are already designing the heavy industrial machinery required to follow them.
And this is where we transition from the theory of a moon base to the physical reality of an industrial operation. The infrastructure currently moving through the procurement and design phases is just massive.
Let's look at the robotics first, specifically the PROMIS rover. The polar rover for observation, mapping, and in situ exploration. The engineering lineage here is vital because PROMIS is heavily based on the architecture of the Mars Perseverance and Curiosity rovers.
Which are incredible machines.
Right. Those are nuclear-powered, incredibly robust platforms that have survived years in hostile environments. But PROMIS isn't going to the moon to look for ancient microbes. Its mission is pure resource prospecting.
It is the ultimate expression of in situ resource utilization, or ISRU. We briefly touched on the tyranny of the rocket equation earlier, but we need to look closely at the math to understand why ISRU is the only path forward.
Let's do the math, because the concept of bringing everything from Earth sounds reasonable until you calculate the mass fraction.
Right. To put 1 kilogram of payload onto the surface of the moon, you need dozens, sometimes hundreds, of kilograms of rocket fuel just to break Earth's gravitational pull and execute the trans-lunar injection burn. If your permanent moon base requires thousands of gallons of water for the crew to drink, and thousands of kilograms of liquid oxygen and liquid hydrogen to fuel the return rockets back to Earth, you cannot mathematically launch all of that from Florida. The rockets would have to be impossibly large.
It would be like trying to build an entire city in the middle of Antarctica, but you stubbornly refuse to use the local ice for water, and instead you insist on airlifting every single plastic bottle of Evian all the way from Paris. The logistics chain would bankrupt the planet.
It is an economic dead end. So the only way a permanent presence survives is if it can live off the land. And we know from orbital spectrometry that the permanently shadowed craters at the lunar south pole contain vast deposits of water ice.
Right, because those crater floors haven't seen sunlight in billions of years.
Exactly. They act as massive cold traps, preserving the ice delivered by ancient comets.
Enter the PROMIS rover.
PROMIS is designed to drive down into those lightless cryogenic craters. It is equipped with ground-penetrating radar and drills to map the exact concentration and depth of the ice deposits. It is laying the groundwork for the extraction machinery.
But the extraction itself is a terrifying thermal engineering problem.
Yeah.
Let's say PROMIS finds the mother lode of ice. It's sitting in a vacuum at roughly 40 Kelvin, which is just barely above absolute zero. You can't just scoop it up and put it in a bucket.
No, you can't. If you apply heat to water ice in a vacuum, it doesn't melt into a liquid. It sublimates.
It flashes instantly from a solid straight into a vapor.
Exactly. Capturing that vapor, pressurizing it, and then running an electrical current through it, electrolysis, to split the H2O molecules into hydrogen and oxygen gas, and then cryogenically cooling those gases back down into liquid rocket fuel. Doing all of that autonomously in a dark crater at absolute zero is one of the greatest engineering challenges in human history.
But if we solve it, the moon ceases to be a destination. It becomes a gas station. It becomes the primary refueling depot for the entire inner solar system.
And PROMIS is just the tip of the industrial spear. We are also looking at the Artemis Lunar Terrain Vehicle, slated for 2025. This is not the little fold-up dune buggy that Apollo 15 brought along.
Right.
The LTV is a highly capable, unpressurized utility vehicle. It is designed to be operated manually by suited astronauts, but critically, it can also operate completely autonomously when the crew isn't there. It has to survive the brutal thermal cycling of the lunar night, meaning its battery and thermal management systems are orders of magnitude more advanced than anything we've deployed before.
And to manage all these autonomous rovers, supply landers, and prospecting drills, you need bandwidth. Which brings us to perhaps the most critical piece of municipal infrastructure, the Lunar Communication and Navigation Relay constellation. It really sounds like they are laying down the lunar internet and the municipal power grid.
That's exactly what they're doing. You cannot run an industrial operation on a delay, and you certainly can't run it if your assets lose line of sight with Earth. Currently, if a rover drives behind a mountain or into a deep crater at the South Pole, the bulk of the moon physically blocks the radio signal to Earth. The rover goes completely dark.
So plan is to launch a dedicated fleet of relay satellites into lunar orbit. We are essentially building a high-bandwidth municipal Wi-Fi network that allows the PROMIS rover down in the dark crater to beam its ground-penetrating radar data up to a satellite, which then relays it seamlessly back to mission control in Houston.
It provides constant connectivity and redundant navigation to the entire lunar surface. When you combine the commercial FedEx delivery fleet, the Scout PSS zoning data, the Immortal LRA navigation grid, the Lickheath radiation models, the PROMIS prospecting operations, and the orbital communications relay, you are looking at the birth of a complete self-sustaining logistical ecosystem.
Which brings us to the ultimate question. Why? Why are we pouring billions of dollars into building this permanent industrial municipal grid on the moon right now with these specific missions in late 2028? To understand the urgency, you have to pull back and look at the brighter timeline. This isn't happening in isolation.
The broader architecture is advancing at an incredibly aggressive pace. We are looking at the Artemis second crewed flyby in 2026, which will take humans beyond low Earth orbit for the first time in half a century. Following that is the highly complex Artemis III mission, which aims to return boots to the surface. And simultaneously, the commercial sector is matching the pace, with companies like Blue Origin conducting massive structural testing of their Mk1 Endurance cargo landers.
So what does this all mean? It really is a golden age of aerospace engineering. For decades, it felt like we were permanently stuck in low Earth orbit, just doing laps in the space station. Now, the paradigm is shifting underneath us in real time. But the moon, despite all this incredible infrastructure, isn't actually the final goal, is it?
If we connect this to the bigger picture, the moon is the ultimate operational stress test. Everything we're building, the resource extraction, the radiation shielding, the dust mitigation, the autonomous logistics, is explicitly designed as a dress rehearsal for Mars.
Because Mars is an exponentially more difficult physics problem.
It is a completely different regime of survival. The moon is essentially our backyard. It is a 3-day transit from Earth. If a catastrophic failure occurs, say an oxygen scrubber fails or a habitat depressurizes, the communication delay to mission control is only about 1.3 seconds.
Right.
You can talk to the engineers in Houston in real time, troubleshoot the problem, and there is a theoretical possibility of executing an emergency abort and getting the crew home in a matter of days. We survived the Apollo 13 explosion precisely because of that proximity.
But Mars strips away that safety net entirely.
The orbital mechanics of Mars are ruthless. Depending on planetary alignment, it is a 7 to 9 month transit just to reach orbit. Once you land, the physics of the solar system dictate that you cannot simply turn around and fly home. You must wait on the surface for roughly a year and a half until Earth and Mars align again for the return window.
And the communications delay is the real killer.
Light speed delay to Mars can be up to 22 minutes each way. If an electrical fire breaks out in a Martian habitat, the crew cannot ask Houston for help. By the time their distress call reaches Earth, 22 minutes have passed. By the time Houston's response reaches Mars, another 22 minutes have passed. A 44-minute round trip for a single sentence. The crew is entirely, profoundly on their own.
It demands a level of operational autonomy that humans have never achieved. If we can't figure out how to mathematically model the dust erosion of a landing plume, if we can't figure out how to reliably melt absolute zero ice into rocket fuel, and if we can't figure out how to shield against galactic cosmic rays while we're only 3 days away from home, we have absolutely zero chance of surviving a multi-year isolation on Mars.
The moon base is the crucible where we forge that autonomy. We are building the commercial supply chain and the industrial machinery there so that when we finally depart for Mars, we aren't just exploring. We are arriving with the proven capability to live off the land.
We have covered a massive amount of ground today. We've seen how NASA's nearly $600 million investment is fundamentally reshaping the economics of spaceflight, transforming commercial companies into a reliable lunar logistics fleet. We've examined the brilliance of forcing those commercial landers to carry standardized instruments, establishing a planetary baseline of scientific data.
And those 3 instruments lay the exact groundwork for human settlement. SCAL PSS, mapping the violent abrasive physics of the landing plume to establish safe zoning distances. The LRA deploying an immortal zero-power navigation grid across the barren landscape. And LATs characterizing the microscopic, lethal barrage of solar and cosmic radiation to engineer survivable habitats.
It is the foundation of a new human economy, supported by prospecting rovers like PROMIS, the Artemis terrain vehicles, and the Lunar Communications Relay. We are watching the transition from exploration to sustained municipal settlement.
We really are.
I'm going to leave you with one final thought to mull over tonight. We are actively transforming the moon from a wild, untouched celestial body into a managed, highly capitalized human suburb. We're laying down the navigation grids, deploying the weather stations, and designing the heavy machinery for resource extraction. But when that infrastructure is firmly in place, when multiple commercial companies, backed by different sovereign nations, are making regular scheduled deliveries and extracting resources, who actually gets to decide the zoning laws in the moon?
That's the billion-dollar question.
Right. If the PROMIS rover discovers a massive, easily accessible deposit of water ice in a South Pole crater, who owns that ice? Does the first company to mine it possess a monopoly on the local fuel supply? Who mediates the traffic on that busy lunar highway? And who assigns liability if an autonomous supply freighter crashes into a permanent communications relay? As we pour the concrete for this new neighborhood, we aren't just solving thermodynamic engineering problems. We're going to have to decide very quickly who governs the final frontier. So tonight, when you step outside and look up at that glowing silver disk, remember, you aren't just looking at a silent rock. You're looking at a bustling construction site, the crucible for our survival, and the absolute bleeding edge of the human future. Thank you for exploring it with us.